Welcome to a lesson with Dr. Powell. Let's find the minimum distance of from the origin of the intersection of two planes. So suppose those planes are y plus z equals 5 and x plus y equals 4, and where they intersect will actually be a line, and we want to find the minimum distance from that line to the origin. Now, there's different ways we could potentially do this. Maybe we could find a vector equation of a line. Maybe we can do a few things here to work with this using vectors. However, we're going to use the method of Lagrange multipliers with two constraints. I picked a simple example so that we could kind of work through the details without too much trouble here in the video. But at least we'll have a sense for how it works. So we have two constraints, and we'll label these as G1, X, Y, Z. So this is like one surface, and you have another surface, G2. And we also have our function that we want to minimize. Now, to minimize distance is the same thing as minimizing this function here, x squared plus y squared plus z squared, if we're distance from the origin, because that's distance from the origin is just the square root of this to find length of a line segment that starts at the origin that goes to a point x, y, z. So we want to minimize the outputs of this function on the intersection of these two curves. So using the method of Lagrange multipliers, what we're looking at is saying lambda f is going to be equal to, or delta f, the gradient of f is going to be equal to lambda times the gradient g1 plus mu times the gradient g2, just like we discussed in the last video. Okay, so let's go ahead and work through that. All right. So look at it this way. Let's take the gradient of f. The gradient of f is 2x, 2y, 2z. It's the gradient of f. Now, let's take the gradient of g1 and multiply by lambda. So the gradient of g1 should be pretty simple here. If we think of this as, it's just going to be 0, 1, 1. But then, instead of writing 1, 1, why don't we just multiply lambda in? Or maybe I'll kind of illustrate it. We have this, but now I'm going to multiply lambda in. So we end up getting lambda. Okay, so this is lambda gradient g1. Now let's do mu times the gradient of g2. Okay, now similarly, this is going to be 1, 1, 0, so 1, 1, but then we multiply by mu, we'll have mu and mu. So essentially, we see our equations right here. 2x is equal to that plus 2y is equal to that plus 2z is equal to lambda. Okay, now in working through this, maybe a nice way to go about this is to kind of solve for our lambdas and our mu's and kind of replace our lambdas and mu's with x, y's, and z's. And then we can use an equation that we get from that, couple it with those two to have three equations, three unknowns. So somehow we want to replace our lambdas and our mu's with x's and y's as much and z's as much as possible. That's kind of the strategy, kind of a nice strategy to use. First of all, we know lambda is equal to 2z. Okay, so we can say, so we know lambda is equal to 2z, so maybe right here. And we also know that mu is equal to 2x. So with that mu and that lambda, maybe we can replace those in this equation here and think about that. So we have 2y is equal to, let's see, it looks like we have 2z for lambda plus, and then we have 2x for mu. And so then, which is the same as writing x plus z is equal to y. Okay, awesome. So we have a nice equation here, which we can couple with these two right here. In particular, I'm going to solve for z here. Let's see, you can use y, I guess, but let's see, with y minus x. Okay, so z is equal to y minus x. Now I'm going to use z is equal to y minus x and put it into these equations here, replace z with it, and we end up getting y plus y minus x is equal to 5. And then we have, okay, and then we have this equation. Let me line up my, let's see, my y's and x's here. Y plus x is equal to 4, or x plus y is equal to 4, but I just kind of lined them up. So this part right here is just 2y. All right, 2y. So you see what I did is I took this z and I just substituted in right there. So y plus y minus x became this right here. So I have two equations, two unknowns. If I just simply add the equations together, the x's drop out. I'm left with 3y is equal to 9, so that I know that y will be equal to 3. Now with y being 3, I can go to this equation here and see that x must be 1, because 1 plus 3 is 4. So x is 1, and that's well determined. X is 1, y is 3. And then using that, let's see, let's find z. So z must be, well, right here, if y is 3, z must be 2. So this tells me that the point on the point where on the intersection of these two planes, where we have this function being a minimum, happens right at x is 1, y is 3, z is 2. That's where it happens. It happens right there, 1, 3, 2. Now, so what is that minimum distance? So you could find the minimum distance simply by plugging this into this function and taking a square root, because this function is the square of the distance from the origin. Or in other words, you just find the distance this is from the origin, right? Because which is the length of the vector to that point. So it's basically just the square root of 1 squared plus 3 squared plus 2 squared. So which would be, so 9 plus 1, so square root of, which would be the square root of 14. And that would be the distance right there. And we're all set. 9, 1, 4. Perfect. Okay, so we just found the minimum distance of any point on these the intersection of these two planes to the origin, and we did it using the method of Lagrange as an example of using the method of Lagrange multipliers when we're dealing with two constraints. Thanks for watching.